right, welcome back. In my previous tutorials, I talked about what is a definite integral, how it works, and how it's finding the area of the curve. I'm going to now discuss how we can use the fundamental theorem of calculus to solve various problems. I mean, specifically, the next part of calculus, integration calculus, is the fundamental theorem of calculus. And we're going to see how this relates to derivatives and integration, how they are correlated together. And that's what's referred to as the fundamental theorem of calculus. Now, before we do this, one thing you probably want to do is write down some properties about integration. So one of the properties is integral from a to b, definite integral of f of x, remember you're finding area of the curve, can equal the integral from a to c. So if c is between a and b, all right, you can find the area by adding the area from a to c plus the area from c to b. So if I kind of draw this out for you, all right, just kind of see with the picture. So if you have an integral, all right, here's my function, we'll call this f, and we're going from a to b, all right, and we want to find this area, and I subdivide this into, and there's a point c in here, okay, the integral from a to b, or a to c, this area, plus the area from c to b will equal the area from a to b of that function. Obviously, the functions have to be the same, and you have to be adding them together. Adding two areas does give you the full area, and that kind of makes sense. The other one I mentioned in the other tutorial is that another property is, how do you know if you have an opposite? Well, if you have an integral from a to b, okay, it's from a to b, so a being the smallest up to the largest. If you switch around this integration, all right, and you go from b to a, because you're going in the opposite direction, all right, we can flip this and make it negative. And what we have is the opposite of the integral from b to a of f of x is the same thing as the integral from a to b of f of x. So those are the two properties of integrals that you probably want to know and we're going to be applying. Now, from here, we're going to talk about the fundamental theorem of calculus. And there are two parts, and we're going to talk about for the first part. The first part is actually sometimes referred to as part 2, all right, but we'll call it part 1. And what we have here is we are going to be finding the integral from a to b of f of x dx, which equals the area from b minus the area from a. Now, also, we're going to be discussing this thing called an antiderivative. A also is known as the antiderivative. But before we get into that, and we talk about that a little bit more, we'll first just talk about the concept of how you use the fundamental theorem, where you take the area of the larger minus the area of the smaller. Essentially, that's how we talk about it. So right here, if we were integrated from a to b of f of x, we would take the area of b minus the area of a. And here's a little example of kind of to illustrate how this works. If I want to integrate from 2 to 7 of 8x, or 8 dx, 8 is my function, and it's a horizontal line, and you can see that horizontal line is right here. That's function a. Now, if I took the integral, all right, and I separated this, so using the properties of what we did talk about up here, so I separate this, and I create another value, and we're going to say that value is 0. All right, so I'm just going to keep it simple. I'm going to start at 0. Well, if I go from 0, all right, to 7, I find this larger integral, all right, from 0 to 7, which is not the entirety of 2 to 7, but it's from 0 to 7, so I'm finding all of this area. Now, to find the area just from 2 to 7, I'm going to take and subtract the area from 0 to 2, right? Because we have to get rid of that area. So if I take the area from 0 to 2, right, from 0 to the lower limit and subtract that, what I have then is the area from 2 to 7, and that area is going to be in blue. That's a little geometry, right? Take the area of the larger minus the area of the smaller. Well, if you look at that, well, that does not equal that, but using what we know about our properties, I have up here, I can actually rewrite this, the area of the larger minus the area of the smaller, and make this so it is equivalent to this. What I'm going to do is I'm going to take the integral from 0 to 7 of 8 dx, and I'm going to make this a plus, but if I change this to the opposite integral, I have to switch, all right, the limits of integration. So now this is going to be 2, it's going to be 0 of 8 dx. Well, now since I have the same function and I have the c value right here, all right, lower and upper, I can actually combine this into the integral from 2 to 7 of 8 dx, which I'm looking for right here. And there you have it. The fundamental theorem part of calculus part 2 is if you take the upper limit area, so the larger area minus the smaller area, you get the area from A to B. Does that make sense? I think it pretty much does. And so this A value, whenever you have a function, you're integrating it, remember, you're finding area. Well, the upper minus the area of the lower, all right, from A to B, and that's why we have this right here. Now, another thing that you probably should know is that this A, yes, stands for area, but it also can stand for what we refer to as, all right, the antiderivative. So here is the concept, all right, if you integrate from A to X, all right, the area of X, the upper limit, minus the area of the lower limit, that will give you your area here. Now, to apply this a little bit farther, all right, we're going to talk about what is known as an antiderivative. An antiderivative. Now, this will lead us into our fundamental theorem calculus part 1. Now, when you integrate a function like so, essentially, yes, you are finding the area of the curve, but what you also are doing is you're finding what is referred to as an antiderivative. An antiderivative is the opposite of a derivative. Okay, so if I take the integral from a to x of t squared, to find my antiderivative, I'll call that antiderivative a, what we would do is we would take this, all right, a of t, and we would do the opposite, all right, try to find out what is the opposite, the reverse of a differentiation. So one thing that we can kind of think of is if we have x to the n power, some sort of variable to the n power, and we're going to start with the simple power rule. The power rule states that we always subtract 1 and then multiply by the exponent and then subtract 1, right? Well, we're going to do the opposite of that. So to integrate and find the antiderivative, instead of subtracting 1 to the exponent, we're actually going to add 1 to the exponent. And instead of multiplying by the exponent, we're actually going to divide by the exponent right here, and then make sure you add a c because we have a constant of integration right there. So what is a of t in this case? Well, figure out the antiderivative. That means we should have t, all right, to the third divided by 3, and that is our antiderivative with respect to t, and that's what we have. All right, we have our plus c there, all right, but with this, we have our limits of integration. So now we're going to apply what we learned in just the other section. And if I do a dual display, just to kind of reiterate this, we're going to take our antiderivative then, and then plug in our upper limit. So it'd be x cubed over 3 minus, and now we plug in our a value, we would have a cubed over 3. And that would be our integral from a to x. And that's what we have. Pretty cool, huh? So in doing this antiderivative, now the next thing is when we have this antiderivative, how do you know if you did the antiderivative correctly? Because we're doing essentially an antiderivative is the reverse or opposite of a derivative. And that's what integration does. It's the opposite of what a derivative is. It's yes, it's finding area of the curve, but it also is an antiderivative. So what happens, all right, if we would then take the derivative of the antiderivative? And that is where it leads us into the fundamental calculus part 1. Sometimes they call it part 2 or whatever you want to call it. But what would happen if we take the derivative of the antiderivative or the derivative of an integral? Well, let's think about this. Well, over here, if I take my antiderivative, and I would take now the derivative of this entire thing with respect to x, what do we got? Well, this side is kind of hard to do because that's what we're trying to figure out. But over here, we can find the derivative. So we'll take the derivative of x cubed over 3, which is going to give us 3x squared over 3 minus, well, a is a constant, so a cubed over 3 is going to be 0. That's the derivative of that. This can be simplified to x squared. So the derivative of the integral, which is actually the derivative of this, is equal to x squared. And if you notice that right there, that is the function inside with respect to x, which is our upper limit. And that's what we just found out. The derivative of an integral will actually be the derivative of the antiderivative, which actually would be the function you took the antiderivative of, which in this case would equal f of x. Derivative of an antiderivative gives you the function that you took and integrated, which is f of x right there. How I think about, and this is kind of what the fundamental theorem of calculus is I think of integration and differentiation like a ladder. You can kind of think about it this way. When you take the derivative or you find your rates of a function, you're going up a ladder. So if we start with f being our one function and f prime is our second one, f squared is the next, or f double prime, f triple prime, and we can keep on going f to the, all right, quadruple prime, and so on and so forth. We climb up the ladder with differentiation. But guess what we can do with integration? When we integrate, all right, our function with respect to x, we go back down the ladder. We go back down the ladder. So if we integrate the fourth derivative, we get the third derivative. All right, if we integrate the third derivative, we get the second derivative. All right, if we integrate the second derivative, we get the first derivative. If we integrate the first derivative, we get the original function, f of x. So derivatives go up, go down. But that also means if we find the antiderivative, and once again, let's think about this. If I take the derivative, and this is what this is, if I take the derivative of an integral, so if I take the derivative of an antiderivative, which is this right here, so the derivative of the integral of f to the fourth, which would be the derivative of the, all right, derivative of the antiderivative, which is f to the third, that would give us, all right, the function inside, which would be f derivative 4, the fourth derivative. Hopefully that made sense. All right, we're going to go and do some problems, all right, related to both these fundamental theorems in just a second in the next tutorial. So this is what the fundamental theorem is. Two parts. The first, the larger area minus the smaller area, and the second part is if you take the derivative of an integral, it always equals a function right inside. All right, we'll talk about more of this and how to apply that in our next tutorial.